Let's move into the next chapter concerning thermodynamic cycles. This chapter has to do with refrigeration, heat pumps, air conditioners, all those sorts of devices. So devices that consume work in order to move thermal energy from a low temperature source to a high temperature sink. Now, most of these types of devices will operate on a refrigeration cycle where the working fluid goes back and forth between the vapor and liquid phase. However, water is not the most common fluid for refrigeration. Common fluids are refrigerants such as, well, ammonia in commercial systems. Ammonia is an excellent refrigerant. However, it is toxic, and so it's not used in small and residential environments where there can't be any significant control efforts to detect and mitigate for the toxicity of the ammonia and any hazardous releases. But it is commonly used in industry in large commercial installations. Other refrigerants, of course, R134A has taken over as the refrigerant of choice for cars. R410A is beginning to get a good foothold in the market for residential heating and cooling. R22 is an older refrigerant. Your house may still use R22 in your air conditioner system. And of course, R12 was what was used in the past for cars. There are others as well. It turns out you can use propane, butane. There's all kinds of chemicals that can be used as a refrigerant. It's just a matter of finding the right refrigerant for the right temperature differences. So we're going to talk about these types of devices, and we won't really make a big distinction between refrigerators and air conditioners, although you may. If you think about the goal of these devices, both a refrigerator and an air conditioner have the task of moving thermal energy from a space that we want to keep cold. A heat pump, on the other hand, is a device whose job it is to keep a space warm. So, for example, my heat pump keeps my house warm during the wintertime. So heat's leaking out of the house, and my heat pump takes thermal energy from the outdoors, pumps it up to a higher temperature, and deposits it then in my home. And so the heat that I get from my heat pump, I don't have to pay for all of it, right? Because all I'm doing is paying for a certain amount of electricity to pump thermal energy into the home. So the goal of the two devices is different. The goal of a refrigerator is to cool a space, whereas the goal of a heat pump is to warm a space. All right, so we need to talk about tons. When you start talking about refrigeration capacity, you'll find very quickly that the capacity of a system is measured in tons. What does that mean? Well, if you have 1 ton of water, and that water is at the point where ice crystals can begin to form, so it's saturated. It's you could call it a saturated liquid, but it's, instead of talking about saturated vapor versus saturated liquid, we're talking about a saturated liquid on the solid and liquid diagram. And so let's say you have 1 ton of water, and it's at 0 degrees Celsius, okay? If you have a refrigeration system that has a 1 ton capacity, what that means is that that refrigeration system could take that ton of water that's already at 0 degrees but not solid and transform it into solid water, all ice, at 0 degrees Celsius. That's what it means. So it has more to do with the latent heat of fusion of water than anything else. Of course, the quantity is where the ton comes from. So, of course, the normal situation for thermal energy flow is to go from regions of high temperature to regions of low. If you look at the beaker in the lower left-hand corner, that image, you can see that we've inserted a glass of, say, hot water into a beaker of cold water. The way that heat normally flows, or in other words, thermal energy normally just spreads out, right? So it's highly concentrated in the 95 degrees Celsius area, but in the 10 degrees Celsius area, there's just not as much of it, and so it naturally flows out. So these refrigerator and heat pump systems drive the behavior in the opposite direction. It requires work to do that. So the natural order is, of course, for things to go to equilibrium. So you see the 95 and 10 degree substances coming to thermal equilibrium at 30 degrees. What if you wanted to go the other way? Well, that's where you need a refrigerator or a heat pump. Well, if we're going to develop cycles for refrigeration, let's consider the Carnot cycle. Why not? So the Carnot Cycle refrigerator or heat pump really would just be a reversed Carnot cycle. That's all it really is, right? The Carnot cycle is fully reversible, so why wouldn't we just run it counterclockwise instead of the usual clockwise? And you can see that on the TS diagram here. Why wouldn't we run it counterclockwise and therefore bring in thermal energy from a low temperature source, you see QL there from state 1 to state 2, and then deposit into a higher temperature region, that's state 3 to state 4, that process where QH comes out. So couldn't we just take basically a gas turbine engine and run it in reverse, put work in, and refrigerate? Well, theoretically we could, and so we'd start off with isothermal heat addition from state 1 to state 2. Now, understand this is the Carnot cycle, and if we're going to operate it, what's the reverse Carnot cycle? If we're going to operate it with a working fluid that can move back and forth between vapor and liquid, which is an efficient way to do things, then we'd have to have isothermal heat addition. Of course, the Carnot cycle, or this reverse Carnot cycle, would be drawn relative to a vapor diagram, a vapor dome. So then from state 1 to state 2, we'd have isothermal heat addition. That's not so bad, right? We could do that because if we're under the vapor dome anyway, we could easily maintain a constant temperature as long as we hold the pressure constant, you see. So if the pressure remains constant and we've got two phases present, well, then the temperature is going to remain constant. So isothermal heat addition, no problem. All that will happen is liquid, whatever refrigerant we're using, that liquid would boil off, right? Now, from state 3 to state 4, this constant temperature heat rejection to the high temperature reservoir, would that be possible? Well, once again, we're under the vapor dome. And all we really have to do is make sure the pressure remains constant, which we can do mechanically, and the temperature will remain constant because, again, we have a saturated vapor-liquid mixture. What about the isentropic turbine from state 4 to state 1? Well, that's somewhat problematic because notice that state 1 ends up in the saturated region, right? And so that means we'd have a turbine whose output has a significant quantity of liquid. In fact, it would be mainly liquid, right? So this is not going to work well at all. So the extremely low quality output of the turbine just would not work. If we tried to use a hydraulic motor instead, we'd get closer to something that works, but again, we'd end up with too many gas bubbles and we'd cause trouble that way. So this is not practical. What about the other side where we have isentropic compression? Well, here we'd have to compress a vapor and a liquid, and I don't know of any device to do that. Plus, it'd be difficult to hit state 3 with controls. So the reverse Carnot cycle is not the ideal cycle for a vapor compression refrigeration system. Instead, we'll use the not very creatively named ideal vapor compression refrigeration cycle. And all it really does is it takes advantage of the horizontal movements in the vapor dome for the evaporation and condensation of the refrigerant and adds in, well, it uses the same trick we used in the Rankine cycle. It moves the compression process, which was an expansion process in the Rankine cycle. It moves that compression process from state 1 to state 2 outside of the vapor dome so that we can get a practical compressor that can compress the gas. Okay, so from state 1 to state 2, we've got a gas compressor. And then, rather than bothering and trying to extract useful work in a turbine, we simply replace the turbine on the left-hand side from state 3 to state 4 with a non-isentropic device, a non-reversible device, an expansion valve. We just throttle it. So from state 1 to state 2, we could have isentropic compression. State 2 to state 3, constant pressure heat rejection is not a problem. Of course, the temperature won't be constant, but that's okay. 3 to 4 would be our throttling device or the expansion valve, and then 4 to 1 would be the constant pressure heat absorption in the evaporator. Now, you will want to mark this cycle in your text because you'll want to add some equations around it. I've got them here. The power input required for the compressor is the mass flow rate times the enthalpy change of the refrigerant across the compressor. So you'll want that equation. Another equation you'll want to remember is that the entropy at state 1 and state 2 is the same for the ideal situation. Of course, real compressors increase entropy, so really point 2 is to the right and up a little bit on the pressure curve. But for our purposes, S1, S2, the entropy in those two states are the same. To quantify the heat gained, or the rate at which heat is pulled into the system in the evaporator, take the mass flow rate times the enthalpy change across the evaporator, so from state 4 to state 1. And then for heat rejection into the warm environment, we'll take the mass flow rate times the enthalpy change across the condenser, so from state 2 to state 3. Now notice there's a new type of diagram here. There's a pH diagram. So far we've had PV, TS, and now we have a pH diagram. This is pressure versus enthalpy, and these are a lot more common in refrigeration and heat pump cycles. And you'll notice the vapor dome is still there, but it's skewed. Well, that's just because of the nature of the variable being plotted on the x-axis. So there's still a vapor dome. We're just looking at a different property of the fluid. So if we look at this, the way the cycle looks on this diagram is a little bit different. It makes sense if you stop and think about it. From state 2 to state 3 is the move through the condenser, and that's at constant pressure because the condenser is a heat exchanger, which essentially has open pipes, and theoretically as the fluid flows through it, the pressure drop is 0. Of course there is some pressure drop, but it's small by comparison to the pressure change across the expansion valve and the compression device. So state 2 to state 3 is ideally a constant pressure process. Similarly, state 4 to state 1 is also through another heat exchanger, the evaporator, and so it's also constant pressure. Now one thing that's nice you can see here is on a pH diagram, the constant enthalpy move through the expansion valve is just a vertical line from state 3 to state 4. Now, one of the reasons for highlighting, well really the main reason for highlighting this diagram is so you remember that the enthalpy in state 3 and state 4 is the same. So add that to that diagram if you have your book open and if you're adding these things. Another really important key thing to solving vapor compression refrigeration cycles is to remember that you will need the enthalpy and entropy at state 1. And so those would just be the enthalpies of saturated vapor at the lower pressure. Similarly, you will need the enthalpy and the entropy at state 3. And that would just be the saturated liquid entropy and saturated liquid enthalpy at the higher pressure. Now, a heat pump and an air conditioner share a lot of the same components. Both have two heat exchangers. Typically, you operate these things with one coil or one heat exchanger indoors and the other one outdoors, or say one, if you're talking about a refrigerator, one on the inside of the refrigerator, one on the outside in the kitchen air. But I don't know why you'd want a heat pump. Basically, I guess you'd be trying to make your refrigerator both an oven and a refrigerator, and that's not very practical. But anyway, in a home, such as my home, a heat pump is actually not that much more expensive than an air conditioning system. And I highly recommend you look into one if you ever have to replace your air conditioner in your home, because a heat pump can save you a whole lot of money. When the temperature outside is mild, the heat pump can run and basically pull in 2, 3, 4 units of thermal energy for the price of 1 unit of electricity. And so that can end up being quite a bit cheaper than natural gas or propane. Of course, if it were me, I would continue with a furnace as well, so that as it gets really cold, because around in the area where we live, it gets down to, every now and then it'll get down to negative 20 degrees Fahrenheit, but most of the time it only gets down to about 0 or so in the winter. And this past winter, in fact, we had some very mild temperatures where it didn't even get down that far. I think it may have hit 20 degrees once or twice. No, I know it went below that. Actually, I think we had a day where it was 5 degrees or so. But it didn't last very long like it usually does. In those days, a heat pump just is not very practical, and you'll see why a little bit later. If you look at and trace a cooling mode heat pump, let's look at the lower figure and start there. What happens is you just have the simple vapor compression refrigeration cycle. In fact, that's the case for both of these. But let's follow it around. The high temperature gases come out of the compressor on the right-hand side in the lower figure, go through the reversing valve, and then to an outdoor coil. So after the compressor has compressed the refrigerant, it's hot. And if you run it through a heat exchanger outside, even if the outdoor temperature, say, is 100 degrees in the summer, the refrigerant's going to be at 120, 130 degrees. And so heat will flow from the refrigerant to the outdoors. Now, once the refrigerant has gone through the outdoor coil, typically it's controlled such that the refrigerant comes into the outdoor coil, which would then be called the condenser. It goes into the outdoor coil as a gas and comes out as a liquid. In other words, you have a high enough pressure where even though the temperature can end up being 105, 110 degrees of the refrigerant, it will still end up being a saturated liquid because the pressure is so high. So that black line comes out of the outdoor coil and feeds into the expansion valve or the throttling device. And what happens there is the pressure of the refrigerant is dropped. So the liquid, quite a bit of, well, not quite a bit, usually 10 to 30% of the liquid will boil off, and in the process cool the bulk of the refrigerant. So now the refrigerant's cold. Now typically you don't want the refrigerant to get down to freezing temperatures. The reason is because you then run the refrigerant, the fairly cool refrigerant, through the indoor coil, and if the refrigerant is at some temperature below the freezing point, any water in the air that's cycling through the unit will freeze, and so the coil will freeze up. One interesting thing that can happen when an air conditioning system is losing its refrigerant, if there's a leak somewhere, what will happen is the indoor coil temperature will actually go down farther. It'll go down to the point where it does in fact ice up. And so if you have a repairman come and he says, well, you got ice on your coil and you need more refrigerant, you might think, wait a second, seems like the refrigerant's working great. I mean, after all, there's ice on the coil. Wouldn't that mean there's too much? Actually, that's not the case. It means there's too little. You want to add refrigerant so the temperature doesn't drop quite so far and block flow across the indoor coil, because then your air conditioning system doesn't work right. So anyway, typically you want the refrigerant to go down to 45, 50 degrees, something like that, maybe 40 degrees, but you want it to be controlled so that as water moves across, or I'm sorry, as air moves across the indoor coil, it's cooled, and then the refrigerant that has gained energy goes back to the compressor. Now you wouldn't want liquid refrigerant going back to the compressor. So in this case, the indoor coil would be known as the evaporator, because what's going on is the rest of the liquid refrigerant is being boiled off by the air. Heat is flowing from the air that's in the home to the cold refrigerant, boiling off that refrigerant. Now notice that the refrigerant temperature remains constant, which is an interesting thing. You want to make sure that liquid does not return to the compressor, because there's a couple reasons. First of all, compressors don't like compressing liquids. That doesn't work very well. Another reason is that the liquid refrigerant represents cooling capacity that would be unused, and so you want to make sure you have some type of device to allow only vapor to exit the indoor coil, which is also again called the evaporator, because that's what it's doing. It's evaporating the refrigerant. Now in reverse mode, in heat pump mode, so look at the figure at the top of the slide, you'll notice that the connections are a little bit different. Now the output of the compressor is routed through the reversing valve to the indoor coil first. Well, this makes sense. That's going to be the highest temperature point. And so what happens is this refrigerant that is in a superheated vapor phase goes to the indoor coil. Its temperature will drop, and the reason its temperature drops and it doesn't just liquefy out at first is because it's superheated, and that's actually the case in the cooling mode as well. It's the reason the outdoor coil incoming temperature can be higher than the outdoor coil exiting temperature in the cooling mode. And of course in heating mode it's the same thing. The indoor coil entrance temperature of refrigerant can be 120, 130 degrees, and it has to go down to the saturated vapor state before the refrigerant can start to liquefy out and condense out and form liquid to exit the indoor coil. Now at this point the indoor coil would be known as the condenser, because that's what's happening in it. The refrigerant is condensing out. Now remember, the refrigerant is still at a high pressure, and so now it has to run through the expansion valve, or an expansion valve. And what you might notice is that there is a direct connection between the indoor and the outdoor coil going through an expansion device. However, typically there are two expansion devices in a heat pump. So for a heat pump, the cost for a heat pump is, versus a regular air conditioner is more complicated controls, the reversing valve, but also typically an extra expansion valve. In my system, for example, there's an expansion valve built in with the coil in the outdoor coil, and one built in the indoor air handler unit with the coil in that unit. So there are two thermostatic expansion valves. And so that increases the cost a little bit, but I ended up buying mine off of a guy on Craigslist that was selling it. It was new old stock. It was a decently efficient unit, and instead of costing, you know, $10,000 or something for this thing, which it was a nice unit. It's a 5-ton, 2-stage compressor. I ended up giving, I think, about $2,000 all said and done for the indoor air handler and the outdoor unit, as well as all the installation and stuff. So it was a good deal, and you can find good deals on these things. And it's helpful to understand this so you know what you're looking for, so you can save yourself some money. So anyway, continuing with the heat pump mode, the relatively low temperature but still high pressure gases go through an expansion valve, and now they have to expand to a fairly low temperature. And one of the problems is that it's difficult to make the expansion happen in such a way that you don't go too low in temperature. And so to really gain heat from the outdoors when it's cold, most people don't really think about turning on a heat pump necessarily when the temperature, say, 50 degrees. I mean, you can, it'll work just fine. But when you really want heat is when it's cold outside, and cold outside means typically below freezing. And so most heat pumps will actually take the refrigerant and expand it to the point where it's below the freezing point of water. And so the refrigerant then goes through the outdoor coil, and of course any remaining water in the air vapor outside ends up freezing on the coil. Now during the wintertime there's very little water vapor in the air, but there is still some. And so heat pumps also have to have some other devices on it for defrosting, because you've got to defrost the outdoor coil. And so what ends up happening is you actually pump heat outside to that outdoor coil in order to get it to defrost quickly. And it really cuts into the efficiency of the heat pump system. So the Achilles heel really of this type of heat pump, which is known as an air source heat pump because the air outside is the source of thermal energy, the real Achilles heel is the fact that that air has water in it. If you could somehow get all the water out of the air before it goes into this outdoor coil, you'd be rich. That's really the problem with heat pumps, because when you really want the thing to work is when it's really cold outside, and partially because of the water vapor freezing on the outdoor coil and having to be defrosted off, but also partially because you're trying to pump thermal energy from a cooler source. Because of those reasons, the heat pump is less efficient. And if you could solve, you're not going to solve the fact that it's harder to raise thermal energy from a lower temperature to a higher. That's just the nature of the beast. But if you could solve the problem of water freezing on the outdoor coil, like I said, you'd be quite wealthy. Often it's not adequate to try and pump thermal energy from a very low temperature to a very high temperature. When I worked for Grody, we needed to do some testing on our parts that would be used on heavy trucks. And so we were making lighting products, and we wanted to make sure that those products would be able to make it through many different temperatures. So we were working we made lights primarily for tractor trailers. Okay, so if you imagine a lamp on the top of a trailer, an 18-wheeler, it's possible that that trailer would need to go, say, from Canada, in a very cool region, to all the way down to, say, Mexico, where it could be very hot. And so that lamp had to be able to survive in that situation. And even, there might be salt spray if they're near an ocean. There might be rain along the way. And so we had these devices called environmental chambers. And an environmental chamber typically was something that you could set whatever temperature you wanted. You could set a temperature profile so the temperature could go up, go down, whatever rate you wanted, within reason. And you could also typically control the humidity inside of the chamber. And so it was kind of like just a small oven is what it looked like. But you could take the temperature down to negative 40 degrees if you wanted to, and you could take it all the way up to 100, 120, 200 degrees. And these were for testing components to make sure that they would work properly. So we use these environmental chambers extensively. And if you think about what you're doing here, well, if you're refrigerating the part and you want to take it down to negative 40 degrees, but you've got room air at 70 degrees, that's a pretty good difference in temperature, right? Negative 40 to 70, well, that's 110 degree delta T, and you're not really going to accomplish that very efficiently with one cycle. So if you look at the thermodynamic cycle in the center, trying to accomplish that with one cycle would be like tracing the outside. In fact, they don't even show Well, I guess they would. Let me trace it around with you. Go from state 1 to state 2, and then up the dotted line to that very tall peak, and then down the dotted line to state 6, on down at constant pressure to state 7, then on to state 8, and then following the line that's not marked, that would just continue the line from state 7 to state 8, down, and then over back to state 1. That would be a simple vapor compression refrigeration cycle, and it wouldn't be all that efficient because the temperature difference between state 1 and that high peak are so large. And so if you instead cascade the system, how would you do that? Well, look over at the left-hand side, and you'll see two different compressor units. You see a heat exchanger in between two separate independent refrigerant loops. So you've got one evaporator at the lower level from state 4 to state 1, and then as you go from state 1 to state 2, the refrigerant becomes hot or relatively warm and goes through the condenser where it can lose its heat to the evaporator of the cascaded system, you see. And so then the upper system can take that heat and pump it up again to a higher temperature to then finally push the thermal energy out to the warm environment. So this is a cascaded system. It is more complicated, but the advantage is that you cut out a lot of compressor work. Go back to the cycle diagram, the TS diagram, and notice that the upper area, that region that has the dotted lines around it, that pink area, represents the decrease in compressor work that's required, because from state 1 to state 2 is the lower compressor, and then state 5 to state 6 is the upper compressor. And so the upper compressor only has to deal with a saturated vapor instead at state 5 rather than a superheated vapor at state 2. And so it ends up not having to raise the quality of the refrigerant quite so high, and that represents a decrease in compressor work. So then if we continue around the cycle, let's continue around the upper cycle. From state 6 coming out of the upper compressor to state 7 is, of course, the heat rejection to the warm environment. From state 7 to state 8, then, is the drop through the upper expansion valve to complete the cycle through the heat exchanger there. If we had a simple ideal system, that line would just continue on down through the lower system. But instead, we've got the cascaded system, and so in reality, the output from state 2 of the lower compressor goes through a condenser all the way down to state 3 instead of just to state 8. So it goes all the way down to a saturated liquid state again before it moves on down to state 4 through the expansion valve. And the pink area under this represents heat transfer that is above and beyond what we would have had in the ideal simple single stage vapor compression cycle. So we do two really good things here. We reduce the amount of compressor work, which means we don't have to pay for as much power to go into the compressors, but we also increase the cooling capacity by cascading these systems. Now that's complicated. It does require a heat exchanger. Well, a mixing chamber, or essentially a flash chamber, is a lot cheaper. And so another way to do something similar is to use a multi-stage compression refrigeration design. And really it's just two chambers, one that separates out and one that mixes. And so the flash chamber on the left separates the saturated vapor from the saturated liquid, allows the liquid to continue on through state 7, expanding again to a lower pressure. And then the little gray box on the right between states 2, 3, and 9 is a recombining or a mixing chamber, so that the superheated output from state 2, the low stage compressor, is mixed with saturated vapor from state 3 before going into the high pressure compressor. And you see what that does is that moves the input to the upper compressor off of state 2 down that curve a little bit to state 9 instead, which saves compressor work. Also, this has the advantage similar to the cascade system I showed you a moment ago, in that state 7 is a move to the left and increases effectively the cooling capacity. So this is a little bit cheaper way to have the advantages of a cascade refrigeration system without the more expensive heat exchanger unit. Now there's also multi-stage single compressor units. You might think of this as your freezer and refrigerator. And the idea here is we don't really have to have just one expansion valve. We could actually have two. If we have two in line with one another, what will happen is the first expansion valve will cool down the refrigerant by allowing some of the high pressure refrigerant to expand, but maybe not cool it down to a really cold temperature. And that way we can have the refrigerator, give up its heat to this refrigerant and then expand the refrigerant again in order to really cool down things and go through the freezer picking up heat. Now you see what's happened here. This is a more efficient design because look at the cycle diagram. Look at all the area enclosed by A456. Do you see that area? QLR is shown there. It's coming in from state 4 to state 5. That area represents work that the compressor does not have to do. And so it's not as good as either of the two former ideas for increasing the efficiency, but if you don't have a real large temperature difference but you need two different temperatures, here's one way to use a single compressor and get some extra energy savings out of it. So this is actually fairly common on refrigerators these days. Another common application of refrigeration is to liquefy gases. And you might say, well, how on earth would you liquefy something like air? How would you liquefy out the nitrogen and the oxygen? Well, you use the gas itself as the refrigerant. It's a fairly clever thing to do. Let's start at state 3, the output of the compressor. Now notice this compressor, what's being shown is a single compressor, but really it's a multi-stage compressor in order to make this as efficient as possible. And you can see that on the TS diagram, those sawtooths going from state 2 to state 3, indicating that there are multiple stages of compression here in order to increase the efficiency, as we talked about multi-stage compression before. But that's all condensed down, all those details are condensed down into one piston cylinder device so that we can concentrate on the rest. And so at state 3 we have a fairly high temperature relative to the vapor dome for the gas, a relatively high temperature refrigerant or gas. Now notice the vapor dome is much lower because these gases that we'd be working with have such low boiling points. And so from state 3 to state 4 is a small amount of heat loss, right? There's not going to be a whole lot here because it's hard to get this gas up to a really high temperature and get a whole lot of heat out of it because the temperatures you have available for cooling are really just outdoor temperatures or maybe some refrigerant from some other process. So we're really not going to get the temperature down very far. We won't really approach the temperature where the gas will liquefy out. But since the gas is at a relatively high pressure and a relatively high temperature, we could cool it if we had some cooled down refrigerant already. In other words, if we had somehow managed to liquefy out some air, the vapor would still be, or that vapor that we've liquefied, well, the vapor that remains in equilibrium with the liquefied air would be at a relatively low temperature. Okay, now I know it'd be either nitrogen or oxygen. I can't remember which one would liquefy out first. But anyway, so if we could pass state 4 across a heat exchanger so that the gas that's returning to the compressor to be recompressed absorbs some heat, well then we could cool down the gas, and that really is the heart of this system, is what's called regenerator. So the move from state 4 to state 5, the way that gas loses heat is by gas that's going back to the compressor that's already very cold. So then from state 5 to state 6 we still have a high pressure but relatively low temperature gas, well it would technically be, it's above the critical point, so it was really becoming a liquid. But anyway, we would expand it out, and what would happen in the expansion valve is the gas would cool down quite a bit in going to state 6. In fact, it would cool down so much that some of it would convert to the liquid phase. Most of it would not, but some of it would. And so we'd end up with some liquefied either nitrogen or oxygen essentially, okay, if we're talking about cooling down air. Now, the interesting thing is that device down at the bottom that separates those two out and allows only liquid to flow out of state 7. So we're going to extract, understand, state 6 is really a mixture of vapor and liquid, but the liquid will fall out by gravity, and so then we could make sure that we just pull off some liquid And that way the vapor above it remains at the same temperature because it's a saturated vapor liquid mixture. And then the vapor can be separated off and go into stream 8. And you see that on the right-hand side of the vapor dome. Now remember, this is a very cold vapor, and so we're going to let it go through the regenerator in order to cool down the gas that has been compressed on its way back to state 9 and then to the compressor. Now because we're extracting some liquid, we'll have to put some more gas back into the system, so understand that's going to increase the temperature a little bit. So from state 9 to state 2, there's a mixing chamber basically not shown between states 1, 2, and 9, and that's why we go from state 9 to state 2. And of course state 1 is just the incoming gas mixing with state 9 to form state 2. So this is a very clever way to liquefy out gases. Now it does take quite a bit of energy to do this, as you can imagine, because you have to take the gas down to a very low temperature. There's another way to refrigerate, and this is something that's commonly used in aircraft. If you think about an aircraft, you really don't want to carry liquid refrigerant around if you can avoid it. And so air is simply used. And it's just basically a reversed Brayton cycle. So you put work into what's now the compressor, which was the turbine before. If you go back to chapter 9, I believe it is, you'll see the reversed or the straightforward Brayton cycle. And then cool that down in a heat exchanger, because once you compress the air, it's going to be relatively warm. Allow that air to run through a turbine. You may as well and extract some work from it and, to help offset the work we put into the compressor. And then the output from the turbine is very cold. Now this shouldn't surprise you. If you've ever used an impact wrench or an air tool, you know that the air coming out of that tool is fairly cold. And that's exactly what's happening here. The turbine is extracting work from the air that's at a high pressure, and so that air has to give it up in the form of thermal energy and flow energy. So anyway, from state 4 to state 1 is where we actually get to cool the cabin of the aircraft, for example. And you can investigate the TS diagrams for this reverse Brayton cycle. I'd suggest you think through these. Absorption refrigeration is another interesting way to do things. If you've ever had a recreational vehicle or you've been in a trailer, you may have had a refrigeration system that ran off of propane. And so it may seem kind of strange that you actually burn the propane and the flame from the propane, which typically you wouldn't see, but you know it's happening. The flame from the propane actually drives the refrigeration cycle and cools the unit, the whatever you've got this refrigeration system in, like I said, typically an RV or something, or a camper. Now how does that work? Well, if you look at the area that's enclosed by the dotted line, that area is really sort of like a heat engine. This area enclosed by the dotted line is really replacing a compressor, right? So you have high pressure ammonia going into a condenser, then going through an expansion valve after it's turned into a liquid so that it can expand and cool, and then going into an evaporator. And that left-hand side looks a lot like the ideal refrigeration cycle, right? The ideal vapor compression refrigeration cycle. It's just that the compressor has been replaced by this heat engine, essentially, that's driving the cycle. And again, I won't go through this in a lot of detail. I would suggest that you put a tab on this page and note the equations that I've got here. But basically, the energy coming in, the solar energy, or usually it's a flame impinging on this, does the work of separating out the nitrogen and the water from one another so that only nitrogen goes through the condenser. The job of the rectifier is to make sure that only ammonia gets through and not liquid or not water. Now there's some other devices here. There's of course a pump for affecting and causing the large pressure difference between the high side and the low side. But the cooling water at the bottom, if you look at this, it's kind of like a heat engine. So thermal energy coming in, the solar energy, and waste heat being rejected in the cooling water, that is generating the work, besides the pump work, to drive this system through. So if you look at the idealized diagrams on the right-hand side, it's backwards, unfortunately, to the diagram on the left. So the reversible heat engine that you see there with the source and the environment, that is the area that's enclosed by the dotted lines, and then the reversible refrigerator is the rest of it on the left-hand side. Now, there's a couple of things that are interesting to me. I'm interested in cold climate heat pumps, and Purdue University actually has a paper out. I've forgotten who wrote it. We'll open it up in just a moment. There's a couple of different papers we're going to look at in order to understand a little bit more about all this. So let's switch over to the documents. I've already got them opened in PDF, and I've posted these for you as well. Let's see, 2006. Written by, I'm sorry, I don't know how to pronounce their names. They're in the School of Mechanical Engineering, so my alma mater. And Air Source Heat Pump for Northern Climates, Part 1, Simulations of Different Heat Pump Cycles. So they went through and they looked at several different heat pump cycles to simulate them and compare them and see which one would be ideal. Now, if you look at this, you'll notice we've got two compressors. Okay, that's interesting. And I believe, if I remember right, I think these allow flow, but I can't remember what they allow to flow. But this looks a lot like the systems we've seen where there are two separate compressors. Now there's a line here, and refrigerant doesn't flow here. This is a control line so that the amount of expansion allowed is controlled by the quality of what's coming out here. You want to make sure that what comes out is a saturated vapor only. You don't obviously want liquid, but you don't want it to be superheated either. That reduces efficiency. So anyway, you can see the cycle diagram there. It's a pH diagram for a two-stage with intercooler. I don't remember the details. You can read the paper. I just wanted to point out that since we're at Purdue, that there is ongoing research and work being done in this topic. What I really wanted to show you was this one. This one's pretty clever and interesting. This is a little different than what we've seen so far. It's similar in the sense that it has two compressors, but look what they're doing here. It's really clever. They take the output that's at high pressure and relatively high temperature, and they allow some of that refrigerant to expand. Now, they run that then through what they're calling an economizer, and this economizer is just a heat exchanger. So you've got relatively cold refrigerant that cools down the rest of the hot refrigerant going through here. And then that refrigerant, its cooling capacity has already been used, so it's put in at an intermediate pressure in between the two compressors. But now you've got refrigerant that hasn't expanded yet. It's still at full pressure, but it's cooler. And so when it expands, it really drops to a very low temperature. So they're generating a very low temperature for the sake of operating this in a cold climate. You know, if the temperature outside is negative 20 degrees, then you got to have refrigerant much colder than that, say negative 30 degrees, for it to pick up heat from the outdoors and be useful for putting indoors. So before it goes to the outdoor evaporator, it's cooled down and then expanded, so it's very cold, to then pick up heat and go into the compressor. So this is a particularly interesting cycle, and I hope you'll recognize it again in a moment. There was a third cycle that they looked at, a cascade cycle, and this is exactly what we saw as the first variation on an ideal cycle, where you had two compressors and you have an intermediate heat exchanger, and this is just a classic cascade system with, of course, a thermostatic expansion device here to make sure that the output of each of these heat exchangers are saturated vapors, and so you end up right on the saturated vapor line. I wanted to point that out because I found it interesting, thought you might like seeing it as well. Now let's go to an analysis where they actually tried one of these. So if you look at this diagram, this is your standard heat pump diagram, and if you consider what happens as the ambient or outdoor temperature changes, well, as it gets colder and colder outside, the heat loss from the environment or the dwelling goes up, right? The colder it is outside, the quicker your house is going to lose heat, right? That just makes sense. Because you're going to want your house temperature to remain constant, say 70 degrees or something. Now, it turns out that that's a problem for heat pumps, because a heat pump, as the outdoor temperature goes down, the amount of cooling capacity that it has decreases. So you finally reach a balance point where the heat pump can only supply heat at the rate that the house needs it. It's just barely keeping up. And if the temperature outside gets any colder, well, then you lose heat out of the house quicker than the heat pump can pump it back in. So the temperature inside the house will go down. And that's bad, of course. You don't want that. So here's a so-called boosted air source heat pump. This was actually the second cycle that we saw in that Purdue paper. And what's happening here is exactly what you saw. Now, it looks a little bit different, but it's the same as before, where some of the refrigerant expands and gets cold. so that it can cool the bulk of the refrigerant that's passing through the economizer. That way, this refrigerant turns out being fairly cold before it expands. Now, the way this is shown, if you look at the flow direction, I actually like the Purdue paper a little bit better because what's shown in the Purdue paper is a cross flow, which is a little more practical. This is showing parallel flow. You would actually want reversed flow. You'd want, what's the name of that? I guess just reversed flow. So imagine this stream actually coming in the other side of the heat exchanger and the outgoing stream coming out this side to continue. Yeah, that's a detail from heat exchangers, so don't worry about that too much. The point is you end up with refrigerant here that's at high pressure but relatively cold, so that when it expands it gets really cold and can pull in thermal energy from the outdoors despite the fact that the outdoor temperature may be quite low. So then it goes through the low stage compressor. The result is mixed with the refrigerant that's already been expanded and used. It doesn't really have much refrigeration capacity, and then goes through the high stage compressor up here. So that's the cycle, and it's really a clever, interesting cycle. I was interested in a cold climate heat pump when I was searching for a heat pump for my home. I knew about this, and I thought, well, I'd like to have something that would work very well in a cold climate. Because see, here's what happens. When you have a single compressor, here's the line from before. When you have two compressors, you can increase the efficiency, but when you have this economizer, you can really end up with a much higher capacity heat output. That's what this red curve is, despite relatively low outdoor temperatures. And so it moves the balance point down quite a bit. And so you see the balance point with the economizer going all the way down to 0 degrees. That sounds wonderful, right? That means that the heat pump can actually pull in thermal energy from the outdoors even though it's cold outside, and even though it's quite cold. So I've forgotten what company it was that did this. I looked into the company and I was trying to buy one of their units. It turned out they were out of business because the Achilles heel of heat pumps apparently is what really caused trouble. So the question was, okay, theoretically on paper this looks pretty good, but how would it really work? When it's installed, what would its efficiency and actual capacity and reliability be? And so they actually installed several, it looks like at least 5 units. I don't know if they had multiple units in these areas or if it was just 1 unit per town or something. But they measured the seasonal coefficient of performance, so the amount of heat out versus cost for, well, quantity of electricity in. I'm sure these were electrically driven. And then they plotted them versus outdoor temperature. And so they noted that there's room for improvement, right? These coefficients of performance are actually fairly low. So if you get a 1.3 coefficient of performance, that means that, 0.3 parts of that 1.3 came from outdoor heating and 1 part came from the electricity you paid for. This is not much better than just having heating strips. Apparently, this did meet the occupants' comfort needs and without ever using resistance elements. So that was good. This is better. All of these are better than just, hooking up a heating element and running current through it and basically burning electricity. But there's room for improvement. So then they went on and talked about energy savings potential and what could be done in various locations. There is another type that's becoming popular today. They're variable speed compressors. You might have seen these outside of commercial or some home installations. And the way these work is instead of having one centrally located expansion device, instead you have one outdoor compressor, which is an expensive component, but you have multiple. It's almost like registers you hang on the wall. And the nice thing about this is instead of having ductwork going throughout the home or the business or whatever, you can have small refrigerant lines because the refrigerant lines are actually very small by comparison to ductwork. It's easy to route them through a building. This is especially beneficial for retrofitting where you need to increase efficiency, and that's why these things have become so common and popular. The downside is that these register units look kind of strange on the wall. People don't really like them, but one of the typical technologies used here is 2 things. Zone control. So if you think about it, if you go to bed at night and you need to, say it's summertime, you want to keep your bedroom cool so that you can sleep, why would you cool your living room and your kitchen and so forth, right? Just let those heat up during the night and only cool the area where you need cooling. That can actually significantly increase efficiency. And so that's one parameter that's usually used here to increase efficiency. Another is variable speed compressors. So instead of the compressor pumping at just one speed and full refrigerant flow, if you can vary the speed of the compressor, you can actually save quite a bit of money when the load is fairly light. You don't really need refrigerant running around like crazy when it's mild temperatures outdoors. And so by varying the speed of the compressor, you can increase efficiency. So I've got there's a few links in this. If you're interested, there's a paper written. And unfortunately, these are no longer manufactured. They went out of business. Now, the reason, of course, they went out of business is that the Achilles heel of heat pumps kicked in, I'm sure. One of the things these devices would have to do is defrost the outdoor coil. And they'd have to do that often. And by doing that, they lose a lot of efficiency. All right, now this idea of variable refrigerant flow has come up against kind of the granddaddy of efficiency, which is geothermal heating and cooling. Instead of using the air as a source and a sink for thermal energy in winter and summer, what about using the ground? Because the ground is this massive amount of thermal capacity, right? And if you could exchange heat with the ground, well, if you go down far enough, I don't know if you've ever been in a cave in the winter or summertime, but it remains the same temperature year-round. And so down in the ground far enough, even without a cave, the temperature will remain constant if you get down far enough. Around in this area of the country, southern Indiana, it's about 55 degrees or so. So geothermal is this idea that, hey, why don't we take thermal energy during the summertime, stuff it into the ground in the summertime, and in the wintertime, pull it back out. And you can do that. That's what geothermal is all about. And there's several different geothermal type systems. You can do what I want to do at my property, which is drill holes into the ground about 200 feet, run pipe through it, and exchange heat with the ground down at that low depth. Another option is if you have a pond, you can simply put a coil out in the bottom of the pond. If it's deep enough and big enough, you can actually exchange heat with that and get a fairly efficient system out of it. There are other devices using well water and horizontal loops, all kinds of different pros and cons for all those. I'll let you look into them, but I'll tell you a personal story. One of my sisters and her husband bought a home a few years ago that's quite a good size. It came with a geothermal heat pump, and they weren't really thinking about that. They just liked the home. And they were moving from their starter house, their small, I think it was probably a little 800 square foot house, something like that they were moving from. And they have, I was, of course, looking at their home as they were considering purchasing it, and I was telling them, hey, it's got this geothermal system, this thing's amazing, you don't know what it can do, and they didn't seem all that enthused by it, but they bought the house, and they liked the house. And they told me that they really liked the geothermal system because they actually pay less for heating and cooling in their large home than they did for their small 800 square foot home. And it's a testament to how efficient geothermal really is. Well, I think it was back in 2008, Climate Master, which is a big geothermal heat pump manufacturer, and another manufacturer, I'm not sure exactly what their name is, they did some upgrades to the ASHRAE headquarters building. ASHRAE is a big, I don't know what to call them, group that you can join. American Society for Heating, Refrigeration, Air Conditioning Engineers, I think is what it stands for. And it's kind of the go-to organization, that's what I was looking for. It's the go-to organization for heating and cooling, whether it's home, commercial, residential, whatever. They're kind of like the standards organization for that industry. Anyway, their building needed some updating, and so Climate Master installed geothermal systems in the second story, and the other company, which made variable refrigerant flow equipment, installed equipment in the lower floor. And they ran this for years and took data to see which one was better. It was kind of like a race between the two titans. It was geothermal versus variable refrigerant flow. And Climate Master wrote a paper saying how well geothermal had performed and outperformed variable refrigerant flow. Of course, that's not good enough, so the company that installed, or that manufactured, I suppose, the equipment for the first floor had to write their own paper and say, well, can this energy efficiency really be compared? So they're kind of halfway admitting that, yes, I mean, how do you argue with the fact that the electric bill for the upper floor was less than the electric bill for the lower floor? Yeah, you can't, right? But can they really be compared? And so they came out with this technical article in 2013. I'm sure there are intermediate articles I missed along the way. Then Climate Master, in I think it was 2016, wrote another rebuttal to this. And it's kind of like they're just going back and forth. It's really interesting read if you ever get the chance. I've posted these for you, so if you look, I've posted all of these documents. Here's the original document, and I've forgotten when it was written. Let's see if we can find a date. Here it is, 2013. Is that the one I was looking for? Yeah, 2013, and then here's the article from the other company from also 2013 claiming why you can't compare the two. And then they've got some valid points, but I still think that the geothermal system would outperform the variable refrigerant flow simply because you're exchanging heat with the ground rather than with the air. And that's advantageous because of the temperature of the ground remaining constant. I'm showing you all of this not because I want you to get into this argument and look at it and decide who you think is the best, but because as an engineer you are quite likely to be part of a significant building project. I know when I worked for Amatrol, they moved from their building about a year after I started to a brand new building. I wasn't actually involved with the building project, but several of the guys in my engineering group were. And one of the things that you may want to consider, if you're going to build a large building and tear up a lot of ground anyway, you're probably going to have a large parking lot. Well, most likely the ideal place for a geothermal system is in that parking lot. You can actually, before you lay down the parking lot, you could drill vertical bore holes. You've got a large area, so you've got a large thermal mass available where you could exchange heat for a fairly large building. And so to me, if you're going to build a large building, the best thing to do is to build a geothermal field right next to it under the parking lot. Why not? It's space that's going to be unused anyway except for parking. So I hope you'll consider that if you're ever part of a large building project. Do consider geothermal. It is expensive to put the heat exchanger in the ground. In other words, regardless of whether you do horizontal loops or vertical bore holes or whatever, it is expensive. That's going to be the major cost. But it turns out the Galt House in Louisville took on a building project several years ago. I think it was in the 80s or so. And at one time, they may still be, I don't know. At one time, they were the largest geothermal installation in the world. They pump water from the aquifers down at about 600 feet and use that water to extract thermal energy or to put thermal energy into it. And the Galt House is a large hotel and office complex in downtown Louisville. They wrote a paper about that experience, and even back in the 80s, they said that they spent less money on the geothermal system than they would on a conventional system, and they saved $20,000 per month from this system. That is a huge savings. So they spent less for the equipment, and they saved $20,000 a month, and they've been doing that since the 80s.